Right, so what we covered so far, I talked about the filtering problem in discrete time, and I made a comparison between the filtering problem and data assimilation, and sort of the gist of the discussion was to convince you that basically these are two facets of the same coin. We all try and do the same thing. And then I spent yesterday time on proving this theorem, which is generic in the sense that it can be applied to any framework, and not necessarily. Oh no. So right. So yesterday, as I said, I spent time proving this theorem, which was quite general. So today the aim is to introduce particle filters. I've introduced them already, and you've seen them in different guises already presented several times. So I'll spend more time today on describing particle filters, generic particle filters. And then I'll try and show you how you apply the theorem to prove that they converge as the number of particles increases. And once I do that, I'll have a discussion on first of all how you how you can improve particle filters, how you can optimize particle filters, what can you do to apply them in data assimilation, and then I will conclude with an applications to a high-dimensional situation where we look at the observed Navier-Stokes, and I'm going to try and convince you of the opposite that Ramon told you, that particle filters do not work in high dimension. I'm going to try and convince you that the particle filters do work in high dimension, and then perhaps we have a discussion to see, what are the differences between the two viewpoints. Okay, so firstly, this is just to introduce them briefly. I'm going to introduce them as a way to show you how you can apply this generic theorem. And the idea is, for any particle filter, the idea is that they involve a system of particles that evolve according to the law of X to start off with, and then we're going to change that, and then you'll see how this can help you to optimize particles in data assimilation. And then after each mutation of the system, after each mutation, the particle mutate, and after each mutation, the system is corrected. Then the correction mechanism consists in replacing each particle by a random number of particles whilst keeping the total number of particles fixed. And this random number of offsprings that each particle has will be proportional to the likelihood of the position of the particles given the new observation. And then we'll see that, imposing some weak restrictions on the offspring distribution on how you assign offsprings to each particles, then you have this convergence as the number of particles increases. And just to remind you, pi t, the approximation for pi t is denoted by pi tn. So, and the approximation for pt, this is the predicted measure, is denoted by ptn. Okay, so I have to remember not to go there. I did remember. Right. So, okay, so that's it. Right. So this page tells you what to do. Right. So if we understand this page, then we understand everything. Right. So what is a typical particle filter? So it starts at time 0. We do something on time 0, and then we iterate these 4 steps. So you have to iterate these 4 steps, and again and again and again, every time you obtain a new observation, or every time you decide to correct the system. So firstly, you have to sample n times from the initial distribution of the signal. So pi naught is the initial distribution of the signal, and the reason why pi naught, the pi, I'm using pi for the initial distribution of the signal, and pi is also the posterior distribution. The reason is not a mistake, is because at time 0, the prior and the posteriors are the same. I assume that I have no observations at time 0. Somehow, if there were any observation of time 0 in data assimilations, as everybody knows, I'm using this observation to generate a meaningful prior. So I'm assuming that there is no observation at time 0. If there was one, I'm using it to get a meaningful prior for the signal. Okay, so, and I have to assume that I can sample from pi naught. So pi naught is a minimal to sampling, so I'm sampling n times from pi naught, and this n samples will be the initial positions of the my system of particles. Okay, so that's what I do at time 0. And now, as I said, I'm going to do these 4 steps, repeat these 4 steps again and again and again till I come to the current time, if you want. So this is an iteration going from the time t minus 1 to t, and at time t minus 1, I assume that I have these positions of the particles, right? xt minus 1 with the index I, right? And these are the positions of my cloud, the position of the particles that make up my cloud of particles. And then I have to explain to you what happens, how do I get from this position of the particles to the position of the particles at time t. So this is the steps that is going to be repeated. Okay. So the first thing, so these are the position of the particles. So the first step is the disputation step. This is the step where I use the transition kernel of the signal to get the new positions of the particles. So the mutation step doesn't involve the observation to start off with. The mutation step simply involves the model, and all I do here is to take the position of the particle and look at the probability measure corresponding to this position of the particle, and then sample from this kernel, and that is going to be the position of the new particle. And for those of you in data assimilations that are used to the alternative notation, that are used to the alternative notation that xn plus 1 is equal to f of xn plus my noise xin, right? So how do I sample? How do I get the new position of the particle, knowing that the model is given by this? Say this is normal with mean 0 and variance 1. I work with my toy model. So all I do is, here is the position. I plug in here the position of the particle at time t minus 1, the ith particle, right? I add this. I use my computers to generate a random number with Gaussian distribution mean 0 variance 1. I add it to this, and I get the new position of the particle, and this is going to be denoted by, I have to put a bar here because this is not going to be the final position. It's going to be, I have to do something to it. But this is how I mutate my particle. This is how I push my particle forward, right? So it's a very simple thing. So, so the, sorry? T. Okay, so at the end of this step, I will end up with a new cloud of particles, and at the end of this step, I will end up with, if you look at the empirical distribution of this new cloud of particles, the empirical distribution of this new cloud of particles will be denoted by PTN, and this will converge to PT. This will converge to PT. Okay, so that's the thing in my theorem that had all those lines. This is the intermediate thing that will give you the convergence to PTN, to PT. Now the point that I need to emphasize here is that so there may be some misunderstanding between what Ramon told you, that what you do you take the approximation at time n minus 1, sorry, at time t minus 1, you push it forward. You push it forward with the kernel, and then you sample from here. N times. So Ramon told you that this is what you do. This is not what you do. You should not do this, right? So what you need to do, you need to push every particle forward with the kernel and sample it from the particle. This is not the same, because This means that you take the whole the whole distribution, you push it forward with the k, right? You now get a sample, a linear combinations of distribution from which you need to sample. And that is not the same thing. It's the difference between normal sampling and stratified sampling, right? So for stratified sampling, you sample from each of these guys. For normal sampling, you sample directly. Sort of, something like that, right? So people in data assimilations do the right thing, right? Do not worry about this. You are doing the right things. You push every particles forward, right? You do not push the entire approximation forward with the k and then sample for it. That's the wrong thing to do. But you do not do that. So you know. Yes, I know. But we can talk this. We can talk afterwards. I can show you that this is the wrong thing to do, but we can talk afterwards. Good. Right. So word of caution. I mean, the data assimilation people are doing the right thing. There's no problem with this. Every particle should be pushed forward. Okay. Now, once you push the particle forwards, then you have to assign to each particles the corresponding weight. So each particle gets their weight according to the likelihood of the position of the particles. So we have this GT. We have the GT that comes from the likelihood of the observation. So remember in our model YT was h of xt plus wt. Okay. So and this one had a density, and so the likelihood of the particle of this particle will be given by the unnormalized likelihood. So will be given by this quantity in here, and I'm going to write it. So I'm using the same notation. So it is g of xti minus So it's g of yt minus xti bar. Okay, so that's the likelihood. Everybody does this. You compute the likelihood in the standard way, and that's the weight of the particle. Okay, so you get the weight of the particle, and then you have to normalize it so that the sum of the weights make up to 1. Okay, so at this point in time, we mutated the particles, and we assigned the weights of the particles. And then now, at this point in time, I want to correct the system. The correction of the system, what the effect of the correction of the system is that in the position, after the correction, somehow the observation will be embedded in the position of the particles. So this is the assimilation step, this is the analysis step in data assimilation, okay? So how do I correct the system? So I did this. I'm going to be very worried here that I did this diagram here. So suppose you have just 4 particles, and these are the position of the particles, and suppose you computed the weights, and the weights of the particles are this, right? They sum up to 1, right? 0.6 is this one, 0.3 is this one, 0.005 is this one, 0.005 this one. The sum of them is 1. Okay? So now I have the weights, and now I want to replace each of these particles by a number of offsprings, which is proportional to these weights. In fact, the constant of the the average number of offsprings will be proportional to these weights. Right? So what I want to do, because I want to end up with 4 particles, I multiply each weight by 4, right? And I get these numbers, 0.2, 0.2, 1.2, and 2.4. And I'm saying each of these 4 particles will have a random number of offsprings, so that on average, in mean, I get 0.2 offsprings for this one, 0.2 offsprings for this one, 1.2 offsprings for this one, and 2.4 offsprings for this one. Right? Why do I want to do that? Well, I want to do that because if, say, this particles has on average 0.2 offsprings, and each offsprings afterwards will have weight 1 over n, I assign, 1 over 4, I assign the same weight to each of the offsprings, then the mass that I assign to each one of these will be back to the original weight. Okay? So multiplying by 4 and divided by the mass and multiplying by the mass of the Osprings gives me, on average, the weight before. That means that this weighted distribution and the new distribution which will approximate pi Tn, the new weighted distribution will be unbiased, will be the expected value of that will be this one. Okay, so on average, I will get this one. So if I write here, so if I denote by pi Tn bar the sum with of the Dirac measures, the linear combinations of the Dirac measures with the normalized weights, and pi Tn will be the thing without the bar, what will happen after I do this correction, right? So this is going to look like this. So sorry, there's an I in here. Sorry, there's no weight. So this is this, right? Okay. Now what will happen on average after the correction, after I do the correction, I get the probability measure with the weights. So the correction, while doing the correction in such a way that I get close to, I get on average this exact value. Okay? Right. Now this is a good thing because what will mean that this particle is very likely in the view of my data, so I want to keep this particle. In fact, it's so likely that I'm hoping to put more than one particle in here. I'm hoping to put 2.4 particles in there, right? These two particles, on the other hand, are very unlikely, right? The probability that this particle is on the right track, the likelihood for this particle is 0.05, and I don't want this particle. And if I do that, it's going to happen that because, on average, I'll have 0.2 particles put in there, which means that most of the time I'll have no particles in there, which means that most of the time these two particles will be killed. So this offsprings mechanism, this correction mechanism does this thing the right way, exactly because I impose this unbiased condition. Okay, so there isn't a unique way to do that, right? There's many ways to do that. I'm just going to show you one which is the most popular way, right? So this is the one when you do resampling. Okay? So this one explains the offspring distribution. So the way in which you can look at all of them is to describe the offspring distributions for all of them. Now I'm not gonna go over this one. I'm just going to explain how you do this. I'll explain how you do this resampling step, the so-called resampling step. And the point of this is that the distribution of the offsprings by using this resampling step is exactly this multinomial, has exactly this multinomial distribution. So the multinomial sampling is exactly what most of you would know what to do. So what you do, you go back to the original particles, the original weights, normalized weights, and sample 4 times. You have 4 particles. You sample 4 times from that distribution, right, with replacement. And then these are the new particles. So you start with the first particle and sort of you just choose one of these 4 sites. You choose one of these 4 sites. You choose this one with probability 0.05, this one with probability 0.05, this one with probability 0.3, and this one with probability 0.6. And then, it's a random procedure. It will fall onto one of them, say it falls onto this one, and then this particle will have this as an offspring. And you do this 4 times, and then let's suppose that you end up with something like this, and these are the offsprings of each of the particles. Okay, so this is what you do. This is the correction steps. This is the correction steps, and at the end of the correction step, you end up with exactly something like this, with exactly, on average, this number of particles. Okay? Now, this completely describes one particle filter, which was introduced in '93 by Gordon Salmon Smith. It's called the sample impulse sampling importance resampling algorithm, and is one of the most popular algorithms out there. There are many, many other algorithms out there. This is just one of them. And it's just the most popular one because it's very natural thing to do. Okay? Now, so what do I need to say about this? Now, this algorithm is great on average, right? I expect to get those numbers. But the problem with these algorithms is that, you know, for example, if I take this value here, I want on average here, I want to keep this particle. On average, I'll get this value, but because of the way this randomness, the random way in which I assign this, with a very small probability, I may not get this value at all. Right? So you can compute the probability, and with a very small probability, the most likely side, you cannot get the most likely side. Okay? And similarly, at the other end of the spectrum, the least likely side, right, we don't want those particles. We don't want those particles, but you know, with a very small probability, my offsprings may end up exactly there, exactly where we don't want them. Okay? So yeah. Yeah. Yeah, yeah. So the idea is that if I have a good guy and a bad guy, if this one becomes better, it's quite likely that this one, the one that was already good, would be even better. So it's an averaging thing, and because of the mutation step, once you are in a good position, you are more likely to stay in a good place. But it's even worse. And the worst thing is that somehow once you are in a good position, you sort of carry this weight. You know, you have been in this bad position, and you will always look worse than the guy in a better position.
The number of particles are fixed.
The number of particles, they stay fixed, 4. They stay fixed and stay 4. Okay, so how do I improve on this? I'd like to improve on this, and a better way to do this step would be to say, okay, since I know that I have here 2.4, I'm going to put here automatically 2 offsprings, right? I know, you know, I want 2 offsprings there, okay? And then I'm going to put here automatically 1 offspring, okay? And then I'm left with 1 offspring, right? So with that remaining offsprings, all I have to do, I have to put it at random, right, on the 4 places. So I match, so I end up in here with what's left here with probability 0.4. I end up in here with probability 0.2, and I end up in the other 2 places with probability 0.2. Okay? So this is a lot better, yeah? Right? This is called stratified sampling, right? So, and that ensures that basically I don't miss out on putting leaving out on missing out the right the most probable sites. But this is still not ideal because I may end up where, I mean, here I'm just left with 1 particles, but you know, you can imagine that you can left out by doing this stratified sampling with a lot of particles, and as a result of that, you may end up, because you still have to apply the same resampling procedure, you may still end up with lots of particles where you don't want them out there. Okay? And you can do even better than that. And the best way to do this is to design an algorithm that ensures that here I get as close as possible to 2.4. So that means that I'm going to put in here either 2 or 3 offsprings. And here it gets as close as possible to 1.2. So that means that I have to put here either 1 or 2 offsprings with the corresponding probability. And here should take either 0 or 1 offsprings and 0 1 offsprings here. Okay? So there is such an algorithm that does this. It gives you on average what you want, and it makes sure that it doesn't go, it gets as close as possible to those numbers. Okay? So this is, there's two variants of this. One is the branching algorithm, which I introduced together with Terry Lyons, and the other one is an algorithm introduced by Clifford and Fairhead, So I'm going to show you. So this is the algorithm. You'll get the slide, so you'll know how to apply the algorithm. And it has the right properties to prove convergence. And there is another algorithm. There is another algorithm introduced by Carpenter, Clifford, and Fairhead that has the same property. And the property is that in here I introduce randomness. You see, and the problem with introducing randomness is really seen in the convergence rates. It's really seen as it increases the variance of the system. It increases the rate of convergence. So what we want to do, we want to introduce the minimal amount of randomness, and this algorithm really have these properties. They introduce the minimal amount of randomness, and these two algorithms have these properties. The algorithm by Carpenter, Clifford, and Fairhead has been known for a long time, and has been known under the name of stochastic universal sampling. Okay, so all of these algorithms, Sorry?
What were you minimizing to minimize the divergence?
To minimize the variance. So remember my picture. My picture was this. Let me just go back to my picture. Right? So this was my picture. In here, this part, I want to control the distance between these two components in here. The distance between these two components is really controlled by the variance that appears in these particular steps. I want to make the distance between these two components as small as possible. How do I make the distance between these two components as small as possible? I minimize the variance. I try to get as close as possible to this guy. I try to get as close as possible to the guy that has the weights in, right? But I can't get to it perfectly because these weights are real numbers. So I have to add randomness because I have to get to particles. I have to get to particles of mass 1 over n. Now, if I can manage to write those weights in terms of multiples of 1 over n, I'm done. There will be zero, there will be no problem, there will be no error there. But most of the time, my weights, as everybody knows, are, 0.0, 0.57, and so on. So you can't do that. So the way you do that, you apply this randomizing procedure, right? One of these sampling mechanisms, you apply one of these sampling mechanisms, and what you end up with things that are indeed, that do indeed look like this. They are random, right? But they are as close as possible to the right weights. Okay? Now, this is the particle filter, and there is nothing else that I need to add on the particle filter. It's a very simple procedure, and it's very easy to implement. And if you haven't implemented, those of you that work on the theoretical side, do implement it. It's it can be implemented on any platform. You can implement it in Excel, you can use C++, Fortran, your choice. Do implement this and see how it works. It's really a useful exercise to do that. Okay, so now the whole bit of there's like 20 pages of analysis of the particle filter, of all these classes of particle filters, and I'm going to give you the slides for this so that you see what they entail. Let me just tell you sort of what is the idea behind all of this. Now in here, what I do, so this is the error that occurs at the mutation step, right? So this is so here, what I do, ideally, I'd like to take this approximation, push it forward, and get to this because my theorem 5 tells me in the proof that this distance will go to 0, right? So this error is controlled by the error that I incur when I do this stratified sampling, right? So when I sample from each of the kernel, I incur an error because I don't get exactly this thing. I get something which is close to this. On average is equal to this, but there's going to be an error. And you've seen from from the talk of Ramon that this error is of order 1 over square root of n. Right? So that's the error here. Here there's nothing I can do at this point in time, and I'm going to show you how you optimize on this error here. And this is the part which will help you understand why is it that you can work with particle filters in high dimension. So at the moment I just suspend the discussion on this one. The discussion on this one, this is the error that occurs at the correction time. At the correction time, you can, regardless of what you do, the error is still going to be of order 1 over square root of n, because you still have some sort of resampling procedure or branching procedure, right? All you can do is to minimize the constant in front of the 1 over square root of n. Okay, so how do you minimize the constant? You minimize this constant by using this algorithm, which ensures that you have minimal variance all the way through. Okay, so let me now go back. So there's some exercise in here that will help you gradually go and apply the theorem. The important bit here is that in the correction mechanism, if you look, the condition that you have to satisfy on the correction mechanism in order to get convergence is to look at the covariance matrix of the offspring distribution. So you have to look at the covariance matrix of the offspring distribution, and if you impose the condition that the covariance matrix of the offspring distribution is of order n, right? Because then you divide by n squared, because sort of each particle weighs 1 over n, so you'll divide by n squared. The error will be of order, the mean square error will be of order 1 over n, which will give you the actual error of order 1 over square root of n. So if you feel that you can have different corrections, you can have other corrections. You can have corrections that will have deterministic components. You can save times. You can say, you can do things that are not necessarily unbiased, as long as you ensure that this error, this covariance matrix is of order, is the right order. You get the convergence. So the correction is very forgiving, and you may be able to save computational time by using one correction or another. Okay, that's the important thing. Okay, now, so I'm repeating here. This Pn is the empirical distribution. I have the first step is called the importance sampling step, or the mutation step, and these are the notations that I have. I showed you the. Oh, sorry, I'm going backwards. I have the weights, and so this is left as an exercise. It's fairly simple to prove that the error that you have, that you incur, so that the length of that blue line is the mean square error is of order 1 over n with a constant here, which depends on time. And as Ramon pointed out, this constant will increase exponentially in time. Okay? Now, so I showed you the offspring distribution, and the properties of the bootstrap filter. So this is the properties of the first filter. The bootstrap filter is quick and easy to implement. It's very easy to implement the bootstrap filter, and there is a lot of work on showing how you parallelize the filter. For data assimilation, you have to be able to parallelize whatever you do, and there are ways in which you can parallelize. Nothing is perfect, but there is methodology out there to parallelize the filter. It is suboptimal, and I explain the reasons why it is suboptimal. And in here, I have the proof of that, so I'm not going to go for this. You have residual sampling, which is the second procedure that I explained. The residual sampling, if you're implementing again, is going to work, right? And then it's still suboptimal. And finally, you have this algorithm that gives you exactly the optimal correction mechanism, and I gave you the pseudocode for this, and then you'll find out in the proofs the proposition that will show you that you have convergence for this correction mechanism as well. Right. So for this correction mechanism, for the last one. Okay. So it's optimal because, for example, it introduces it has minimal variance. So in here, remember, I want to have a random number of offsprings that gives me on average 2.4. And the best I can do is to have 2 offsprings with probability 0.6 and 3 offsprings with probability 0.4. You know, any other random number of offsprings will have higher variance, right? And there is a unique, I mean, you cannot have a different random number of offsprings that will give you minimal variance and have 2.4 on average 2.4 number of offsprings. So it's unique in that sense.
It minimizes the variance of this random measure amongst all measures whose expectation is exactly the measure you started with and take values in the integer numbers.
Yeah. So among all measures, yeah, so Ramon is right. Among all the measures that can be written as linear combinations of particles of mass 1/4, it has the property that individually for all sides, it minimizes the variance. But it does much more than that. The way in which, if you look at the papers, the way in which is designed, it minimizes the variance of clusters of sites, not all clusters, but a lot of clusters of sites, depending on how you construct the algorithm. And so this is where you can come and say, well, okay, so I have my particles, and I know that roughly on the southern hemisphere and on the northern hemisphere, I have the same mass, and you can choose the right algorithm that ensures that you have the same mass on the southern hemisphere and the northern hemisphere. This isn't something that we could do with normal resampling, because the normal resampling, it just goes there at random, and you cannot control where the particles are going.
I'm going to ask you a sort of practical question.
Yeah.
I have no experience with doing this, right?
Yeah.
But my expectation would be that, there are other ways to reduce the variance, like importance sampling, right? Because here you're still running the original, you're still simulating.
So I'm getting there. This is the first step. Right. This is. I'm going to come back to the second step.
But my question is, heuristically, my expectation would be that any improvement you get from using this sort of optimal sampling instead of independent sampling would be completely negligible with respect to the improvement you get from doing the importance sampling. Right?
Precisely. Precisely. Yeah. So this algorithm is as complicated as any of the others. It just involves the same amount of computation as any of the others. It's just that you have to, the pseudocode, the code for this is a bit longer, and why not using the optimal one? I mean, it's not something that you have nothing to lose in terms of computational effort. Oh yeah. You get improvements, but obviously you can the bulk of the improvements you get from the previous step, from choosing the right mutation, the right transition kernel. So you are right. Okay, so you have here discussion of this, and there is also a discussion where I'm trying to make the point that you shouldn't be worried about fixing the number of particles. Yes, in data assimilation, everybody's fixing the number of particles. You can have situation where it is not a bad idea to let the number of particles vary, and there's some discussion on this. I'm not gonna go into that. Non-constant number of particles does not necessarily lead to instability. You can show that that if you are in the right regime, the number of particles will vary, but not a lot. If the number of particles vary a lot, it means that you are in the wrong regime. It means that you still have not reached the convergence regime. Okay, so you have all these results in here that show convergence. I'm not going to go through them. You can get rates of convergence. You know, there's a lot of methodology, and there's been a lot of work, and there's a whole book by Pierre Delmoral that will show you many convergence results in large. It will show you large deviation, central limit theorems, and so on. So the theory for particle filters, for the analysis of the convergence of particle filters has been developed massively by the French school. So if you want to look into that, by all means do look into that. Here you just have a tiny sample of the results that you have in there. So here is the big point. So particle filters converge. So you have the results for that, and the reason why they converge is because you have you have the right conditions, you have samplings, everything is nice. You can apply all the results that exist. In particular, you can apply the theorem 5, which is a necessary and sufficient, which gives you the necessary and sufficient condition for convergence. Okay. Now, what is the big deal? Why is it that Ramon on one hand tells you you cannot apply particle filters in high dimension, and those that work in data assimilations, they know that they have been applying particle filters in high dimension, and their dimension is not really 1, but is obviously not really infinite, but you know, it's okay to have several hundreds, maybe thousands of dimension. Well, the reason for that is that it's wrong to use, you know, it can be wrong, right? So I have to qualify my statements. It may not be the right thing to use the transition kernel of the signal, okay? You see, in data assimilation, people say, well, we don't really trust the model. We got the observation, but we don't really trust the model. There's a lot of information in the observation, and therefore we should do something to account for that. And what you do is, just because you don't trust the model, you do something. When you do at the mutation step, you do something that ensures that the observations are somehow embedded in the right way, embedded in the mutation step. And the way you do it in such a way so that when you do the second step, the correction mechanism, then the corrections will be very small. The correction will be very small. And there are, now, the whole theory, everything that I told you so far works neatly. It works in the same way, even when you change the KT, the kernel of the signal, with a new kernel. So if you can choose so regardless of what new kernel you choose there, KT tilde, KT bar, right? You can rewrite all the formulae with KT bar. Of course, if you use this KT bar, what's going to happen? The GT, the likelihoods will change now, right? So, you know, when you apply the base formula, the likelihoods will change. The new GT will be equal to the old GT times the ratio of the two kernels, right? But, you know, this is computable, and, you know, you can just apply the same theory with the new GT and the new kernel. You see, the important thing to take, to observe in here is that when you go, let me just go back to.
That's what you call nudging, right?
Yes, I'm getting there. That's exactly nudging. Yes. So. Trying to get to my picture. Right. So remember my picture in the first day. I'm interested to get to approximate these blobs in here, right? That's what I'm interested, right? Now, I can get from this guy to this guy by updating, but by updating with the model kernel, with the signal kernel, and multiplying then by the GT in the way that I showed you. But that's not the only way, right? There are an infinite way in which you can write the formula to go from pi t minus 1 to pi t. Now, you choose your kernel, and as long as your kernel is absolutely continuous with respect to the old kernel, you have another formula to go from one step to the other. There's nothing stopping you to use a new kernel. Now, How do you use the new kernel? That's the crux of the matter. This is the open problem. And there is already a lot of work on this step, on this matter. And sort of one of the standard way that that you can do is to use nudging. So that nudging is exactly this thing. You say, okay, I'm not going to use the model because I know that the model is not perfect. And what I'm going to do, I'm going to nudge. I'm going to move the particles in the area of high likelihood. I'm going to move my particles where the observation tells me that they are going to be. Now, the result of doing this is that your likelihoods G's will not vary a lot. Will begin to be very, very even, right? So you get into the right area. So your G's, your likelihood now is going to be pretty evenly. They're going to be pretty evenly equal. Of course, they may not be quite all of them. You know, your nudging is never going to be perfect. Although Peter van Loven has something where the nudging appears to be perfect, right? So yeah. And then if the nudging is perfect, then you are in very good shape. Now, how is this going to help us in high dimension? Well, remember that Ramon told you that there's a problem with having the infimum of having with things like the supremum over the infimum of the likelihood. Now, if you make this thing close to 1, the deterioration is not going to be that bad. Well, his problem was that he had the W here. The W was the number of sites, the number of observations, okay? So here, no matter how close to 1 I'm going to get it, it's still going to be exploding when W goes to infinity. Well, it's not going to be exploding if I choose my likelihood so that they depend on W. So if I choose this ratio, if I nudge the particle so that the supremum over G for the likelihoods and over the infimum over that is of the form, for example, it has an upper bound of this form, 1 plus K over W. Now, when I multiply by W, no matter how big your W is going to be, it's still going to be less than a constant. And so the explosion in dimension disappears. There is no problem with high dimension, right? And we have 2 papers where we try to show an alternative methodology that does not use nudging, but uses something which is called tempering. How much time do I have? 10 minutes. Good.
I mean, we cannot discuss this in the time that is there. Dan is not going to agree with me, but he is very wrong.
Good. Now, can I finish my,
The solution is easy. You are not allowed to choose G. G is given by the model.
No, that's exactly what I say. You are allowed to use G because you change the K.
No.
Okay, right. Okay, so can I finish? Can I finish my presentation and then we can discuss?
But you're looking at the wrong part of the algorithm where the problem lies.
Yeah. So okay. I just want to show the Navier-Stokes first, and then we can discuss. Right. So now, for the tempering, we do something different. Now in the tempering, we want to. Let me just go to the last part. Right. So I'm making here the same point that Ramon makes. That, for example, if my prior is this, so I'm in D dimension, and I have a normal with mean given by this vector, and covariance matrix given by the identity, and then I look at another normal with mean given by this vector, and the covariance matrix given by this. Okay. Now what happens is that if I look at the total variation between these two guys, the total variation, you can write explicitly what the total variation is equal to twice the probability of a random variable, the absolute value of a random variable, which is normal mean 0 variance 1, being less than d over 2. But what happens is that the total variation between these two between these two random variables goes to, I have to be careful here, goes to 2, depending how, so they become singular as d increases, and then they become rapidly singular. So the picture that he shows you applies that eventually, if d is large enough, you can think of the two measures as being singular to one another, as having different supports. Okay, so it's useless, as he said, it's useless to start with a sample from here. It's useless to start with a sample from here and hope that you'll have some particles in here, so that when you do the resampling, you'll end up with a good description of this random variable in here. In fact, you know, as Peter Bickel proves, is you have to wait an exponent. You have to use an exponential number of particles so that you end up in here, right? Does this mean that particle filters are not going to be useful in high dimension? By no means. It just means that if you try to do this the garden variety way, right, you're not going to get it, right? So what can you do? You either do nudging, which means that you push the particles in the right direction, right? Or you do what I said, you do something which is called tempering. So the tempering methodology works in the following way. You do not directly resample, right, in one go. What you do, you take this random, you take the ratio, you take this and you flatten it, right? So you multiply it. So let me just, I don't know if I have this. What you do, you take this and you multiply it by a constant, so that this gets flattened, right? So instead, for example, instead of sampling from this random variable, which looks like this, I guess has this density, right? What you do, the first step is to flatten it, and you multiply this by 1 over d, where d is the dimension. Right? So what's going to be the effect of this? The effect of this is that all of a sudden I aim to get to a random variable which is a lot flatter, which looks like this, which is almost uniform. Now here in this case, it's going to be no problem. You know, I'll have particles in here, right? And I can do my resampling. And so, you know, maybe some of the particles will disappear, but I'll have enough particles in here in the support of this flattened random variable. And then by doing the resampling, maybe some of these particles will be duplicated. Okay? Yeah. Yeah. This is not nudging.
I know. We're tempering, you're basically saying to the prior, there are more information than this.
Right, but I'm also saying that there is because I multiply by this, I'm saying the information is not really that important. Okay, but I will introduce the information gradually. So you do this tempering, so some of these particles get duplicated, and then what you do, you have to introduce a metropolis Hastings or an MCMC method so that you get back, you know, distinct positions for the particles. And then you do it again, and again, and again, d times. Now, if you do it this d times, the particles gradually are pushed towards the right support. Okay, so this is the paper that we wrote in answer to Peter Bickel's remarks. And this works, and we applied it to the observed Navier-Stokes. So I don't have time to give you details about Navier-Stokes. This is the stochastic Navier-Stokes. You know, I'm showing here how you transform it into a filtering problem. You have the model parameters in here. I've just given you the model parameters, and this is the results that we got. You know, it's not a bad result. We compared it with the MCMC method, and and the comparison is really very good. And of course, the sequential Monte Carlo or the particle filter works much better. Okay, so to finalize, let me just say a few things to the local people, the people here from India. The Indian school has an amazing cultural heritage in this area, in filtering area, and there's been a lot of work, and is worldwide, widely recognized as a great school in filtering, in the theoretical development of filtering in many of this area. Somehow, it is the case that when you go into the numerical applications of the filtering, there hasn't been any major development. There hasn't been a lot of work done by the Indian school, and somehow particle filters, which the development of particle filters has passed by, it's a pity because it's the right place to do it. Here in India is the right place to work, not just on the theory, but also on the applications. I feel that data assimilation is a great opportunity for the Indian school to go into the practical part of filtering, right? There are a lot of open problems. What I told you is just sort of scratching the surface. Of course, by no means we pretend that we solve the problem. There are a lot of problems. It's a very interesting area, and it's a very challenging area. And it will be great if people that have Indian heritage and have Indian background will come into this area and will contribute to the development of this area. Okay, so I'm going to stop here, and I thank you for your attention. And now I can take questions. Go. Well, you, Alberto. Yeah.
One of the points is that in the nudging procedure, which is like the synchronization analysis and the master and the play,
Yeah.
we want that the observation are continuously given to the given system. So in a way or in another, while it's difficult for maybe the other particle filter application to take in mind, we have the observation are discrete.
Yes.
So what you do is make a temporal interpolation.
That's what you need to do. You have to do some sort of temporal interpolation, and in some sense, if you look at the paper on, I forgot. Okay, I'll answer. The paper on tempering is exactly this thing. It tries to put continuous time in between discrete times.
The point is that what we know that at least in the application of the various of the time, that the way how you do this kind of preparation is crucial because in the true time when observations are taken, you are inventing information.
Yes.
So it is not necessarily true that pushing the model toward this time interpolation of the observation is better than letting the model adjusting itself. That's just a comment.
Yeah. So in tempering, the way in which, if you see the paper, the way in which we do it, we added these steps. So between t-1 and t, we invent this artificial time, right? Which you have these steps in there, d being the dimension, okay? And as you take d into infinity, as you go to the infinite dimensional situation, what will happen? You end up with a continuous time thing. So in the limit, the tempering happens continuously. So when d is equal to infinity, you have to do nudging continuously. But d is not infinity, it's finite dimensional, and it works fine if you do it in discrete times, as long as you have something which is proportional with the dimension of the space. Okay, you'll get the PDF files, the PDF file for this, but I need to tell you about the papers. So everything that I said is from my book, from chapter 10. The book is in continuous time, so it may not be relevant to people working in data assimilation, but chapter 10 is completely in discrete time, which covers everything that I said. Okay, there is a handbook of nonlinear filtering that appeared 2 years ago. I think that's ambitious. I think it appeared in 2012. This has a lot of material, including a huge chapter on particle filters. So this is, you may want to look at that as well. this is the paper that introduced the SIR algorithm. If you are a beginner and you want to go into this, this is an excellent collection. This book has an excellent collection of papers that you can read. It's written by practitioners. It's written by people that really applies particle filters or sequential Monte Carlo methods. And if you want to read what happens in the high-dimensional space, you know, how do you address the question that Peter Bickel raised, that particle filters cannot be used in a high-dimensional space? We have two papers. They are on the archive. If they are not on the archive, they are on the website of my collaborators. I don't think I have them, but there you are. Okay, so I'll take more questions.